Okay, so we have talked about active rectifier, PFC based, wherein we have a diode bridge rectifier followed by a DC to DC converter, which boost converter is certainly a popular choice, but there could be any other converter also possibly used, right, for such kind of operations, especially a buck boost kind of converter, right, which is also a fairly good choice for such circuits. Now let us in this video let us try to understand dual boost bridgeless active rectifier, right. So let's start first with understanding what is the limitation of the existing PFC circuit which we have seen, and then how does this new circuit solves that problem. So if you remember, our earlier circuit had this diode bridge, right, followed by a boost converter. This was our PFC boost circuit, right? Now, one of the thing that you would understand here is in active state, in active, or rather let us say when S is on, we as we remember the direction of the current, if switch S is on, the current would flow in this way, right? And from the top to one of the diodes will be conducting, and again from the bottom to one of the diodes would be conducting. So let's say D1 is conducting, so the current goes like this into this, then it comes from here and then goes back, right? So there are three devices which comes into the conduction path, two diodes and a switch. So when S is on, three semiconductor devices conducting, right, and when S is off, the current would flow through this output diode, through the cap, and again from one of the bottom diode and from one of the top diode. So again when S is off, now there are two diodes and plus one three diodes. So again there are three devices conducting. So now the problem is that because there are three devices conducting, there is conduction loss, because there is more conduction loss because each device would have its own on-state voltage drop. If you remember a normal boost converter, right, a DC to DC boost, then you can see that at any instant only one of the semiconductor device conducts, either a switch or a diode. And therefore the conduction loss would be only corresponding to one switch or one diode. But now if there are three active devices or three devices in path, that means there is going to be more conduction loss, right? You can say approximately if the devices have same on-state voltage drops, then there will be almost 3 times of conduction loss, right? Which is not good. So that is the reason, although the top circuit, PFC boost certainly has an advantage because it could rectify, it could maintain power factor, but then people were still looking for better solutions, because when they compare it with a regular boost converter, obviously it's with a DC source and this is with an AC source, but nevertheless, people see that there is certainly much more conduction losses happening in the top circuit as compared to the bottom circuit, right? So with that, people started looking for other circuits. Now, one of the way to think about another circuit is that, look, we are using a boost converter nevertheless, right, in the top red circuit. So why don't we use, so here what happens is we are using a diode bridge rectifier which helps us use a common boost converter, whether it is a negative input voltage or positive input voltage. Why? Because irrespective of the input voltage polarity, you get V1 which is always positive, and therefore you can use a normal boost converter. But what if, let's say we are willing to use two boost converters instead of a single boost converter? Then can we do something? So for example, let's say when the input voltage Vin is positive, in that case, I use a circuit which is something like this, which is like a regular boost converter. Right, well and good. I can control this current. To increase the current, I can turn on the switch. To decrease the current, I can turn off the switch. So I can certainly use it when Vin is positive, right? And I can shape the inductor current as per I want, which is almost a sinusoidal kind of shape, right? I can do a hysteresis current control, which we discussed in the last video. The only catch would be if the input voltage becomes negative. In that case, there is a chance, because the switch has an anti-parallel diode, there is a chance of short circuit happening in this loop which I have just shown you, right? If whenever the input voltage goes negative. So to avoid that short circuit, what I will do is I will add an additional diode here which will avoid that short circuit. So this diode will ensure that the current only flows in one direction. If the input voltage goes negative, then this circuit will not operate and there would not be any short circuit happening also. So it would still be safe, the circuit would be safe and it will not operate. So this circuit, which is half of the circuit, can certainly take care of the positive half cycle of the inductor current. You can turn on the switch, the current will rise. You can turn off the switch, the current will fall when the input voltage is positive. Now, when the input voltage is negative, we need a separate DC-DC converter to take care of that. So now I am drawing that case. This is the reference polarity, but you understand now that the input voltage has become negative. So the lower terminal is actually a positive terminal with respect to the upper terminal. So what I am drawing is I am just still drawing a boost converter, but I am drawing it with respect to the bottom layer. Right, so I have just inverted the source in a way and I have again connected to a boost converter, right? First case the source was positive, the second case source became negative, so I just inverted it and I still connected it to the separate maybe boost converter. So now this can take care of the negative current path, because this current it can control. If you see, this current is actually a negative current, so it can take care of the negative current path. Input voltage is also negative, so whenever you close the switch, the negative current will further go negative. When you open the switch, the negative current will try to come towards zero. Okay, so far so good. So these are so in the second circuit also. Now the problem is, what if the voltage becomes positive? Again, if you see, there is going to be a short circuit through this switch diode, and therefore to avoid that we have to connect a diode in this circuit also. So let us say I connect a diode in this direction so that the current can always flow in this direction but cannot reverse. So this takes care if the voltage becomes positive. So essentially these two independent circuits, if I connect, right, then I can ensure that the current that I'm drawing from the source, I'm able to draw a sinusoidal current. In the positive cycle, I will use switch S1 and D1. In the negative cycle, I will use switch S2 and D2, and I will shape the current. If you try to merge these two circuits, right, just imagine overlapping these two circuits on each other with a common source and with a common output. So let me try to draw it. This is a common source, right, and then it goes to an inductor, and then it goes to a switch S1, goes to a diode D1, followed by output capacitor. And from the bottom of the switch comes through a diode. Let me call it as, let's say, D prime 1, and this is D prime 2. So this is D prime 1. Right, this is the first circuit I've drawn. Now I'll try to overlap the second circuit onto this point. So from the bottom point, let me draw another inductor, draw another switch S2, the diode D2, and then from the negative of the source we connect to the positive terminal of the source through a diode and D2 prime. Okay. This is the circuit which we would get if we combine these two circuits. Let me just bring it down a little bit. Yeah. So that is the reason, if you see, this circuit is called as dual boost. Why? Because you are in a way combining two boost converters, and it's also called as bridgeless, dual boost bridgeless. Essentially the bridgeless here implies that you do not have a diode bridge, right? So that is why it's called as bridgeless. So this is a dual boost bridgeless PFC, right? How does it operate? In the positive cycle, the current you would like to be positive because you want to maintain unity power factor. So you close switch S1, current will flow from this path to this path through D1 prime again to the source, and when you open S1, it flows through D1 through the output DC voltage, and then return path is the same through D1 prime. So when S1 is on, how many devices are conducting? S1 and D1 prime, two devices. When S1 is off, D1 and D1 prime, again two devices. So in the positive cycle, irrespective of whether S1 is on or not, there are only two devices which are conducting. Similarly, in the negative cycle, irrespective of whether S2 is on or not, only two devices are conducting. So you see that one of the advantage as compared to the previous circuit is only two devices conducting, right? I mean, still we certainly could not minimize it to a single device conduction as in case of a single normal boost converter, but we have very well maintained or rather reduced the conduction losses happening in the as compared to the previous circuit in this dual boost bridgeless PFC circuit. So good enough. Certainly if you gain something, you lose something, right? So what you have lost here is in terms of the number of components. So you see, for example, you have these two inductors L1 and L2. One inductor is being used for half cycle. Inductor L2 is being used for second half cycle. You have a diode D1 used for only first half cycle. S1 used for only positive half cycle. So you see all the devices, one is that number of devices are still considerable, right? And plus the devices are still being used for half cycle. It's not that both the inductors are being used for the full cycle. So it is in a way underutilization of the resources that are available to you, right? As compared to the previous circuit, for example, in the previous circuit, yes, the diodes were still underutilized, but in terms of the switch, in terms of the switch, the inductor and the output side diode, they were utilized throughout the cycle. But that is not the case here, right? Especially if you see, inductor is something which is really big and bulky, right? And we would certainly like the inductor to be we would like inductor to be utilized to the maximum. So that is one of the reasons that although this circuit looks good, but has not picked up so much as compared to the circuit that we are going to look into the next video.